Okay, so that's how the what's it called, decoder model works. That's the um, LLMs are basically decoder only. So that was our quick recap. Now, what are we going to do today? We're going to add to make the full transform model, we have to add the encoder, which is on the diagram, is on the left. And this is going to be really easy because we have all these foundational building blocks. Effectively, if we're imagining the decoder as a 5-story building standing up on its own, now we're going to add another building on the left. It's going to be a 4-story building. So a 4-story building is going to have the same thing: input embedding, positional encoding. Then it's going to have level 3 a self-attention mechanism, and then in level 4 is going to have the feed-forward neural network. So all very similar. It just doesn't have that output layer. Now, in order to connect them, we have to make a modification to our decoder model. So let's look at the part on the right again, the model that we were just talking about, or the architecture we're just talking about, the decoder part. So we're going to keep level 1, 2, and 3 intact, so up to the self-attention. Now, after the self-attention, we have the feed-forward neural network, and then after that, we have the linear output and softmax. We're going to lift the feed-forward neural network level 4 and level 5, which is the linear transformation and softmax. We're going to lift them up, and under them, we're going to slot in another level, and we'll call it level 3B or 3.5, as you wish. So we're going to have level 1, 2, 3. It's going to be one of those weird buildings where you have level 3, and then you have level 3B, and then you have level 4 and 5. And so level 3B is another attention mechanism. It's called cross attention. And we'll get to that in a bit. But first, what we're going to do is let's talk about the encoder, so we know how it works, right? So it's got those 4 levels that we discussed. We're actually going to look at an example right away. So to help us illustrate this, we're going to look at an example. Bear in mind, we're talking about inference, not training. We can mention training towards the end, but it will be very similar to how we talked about training for a decoder-only model. So we're going to look at an example. So transformers are basically the original design of transformers. The full model was to translate sentences, right? So that's the use case that we're exploring in the research paper. We're going to look at the sentence: "The cat sat on the mat." It's got 6 words, and we're going to translate it into Spanish, right? So we're going to pretend that this transformer has already been trained on how to translate sentences into Spanish, and we're going to see how it's going to work with this specific sentence during inference. How is it going to translate it? So the correct translation is I don't know Spanish, so I might butcher this, but it's "El gato se sentó en el tapete," right? So the cat sat on the mat. And here, gato is cat, se sentó sat, tapete is on the mat.
Sounded pretty good to me. I don't really know Spanish either, but I buy it.
Thanks, man. So we're going to translate that sentence into Spanish. What happens, right? So the decoder, encoder, right? Let's talk about the encoder first. The building on the left, the 4-story building. All of the English words are going to go into this encoder part. The cat's out on the mat, 6 words. They're going to go through positional encoding. They're going to go through a vector embedding. So so they're going to get their vectors with semantic meaning. Then they're going to go through positional encoding, which we've already discussed. Then they're going to go through the self-attention mechanism. So the whole QKV process is going to happen, and each one of these vectors will get a context. Each one of these words will get a context-rich vector. So now we have 6 context-rich vectors, and then in level 4, each one of these 6 context-rich vectors will go through a feed-forward neural network, and to add some more flexibility, add more parameters, so it becomes even more able to understand the complexities of language and so on. So after that feed-forward neural network, we'll have 6 vectors, which are contextually super rich. Let's call them super contextually rich vectors, or super vectors after being contextually rich, because they went through the feed-forward neural network with the activation function. And we'll call them vectors O for output of the encoder. So those are 6 O vectors sitting there. And we'll just put a pin in that. So we have 6 vectors that went through the 4 levels of the building on the left, which is the encoder, and they're sitting on the rooftop, right? That's that. We have now created a good representation, a very rich representation of our English sentence. And we're going to use that when translating. Now, the main part, in my view, I would call it the main part of this translation process, happens in the decoder, right? So when we like all of the, it's going to be like large language models. It's going to be like a GPT model where we're generating text from a prompt, The only difference is, the best way to think about it is like we're generating text, but with a condition on it, right? So for argument's sake, let's say we've already generated 3 words. So out of our sentence that we need to translate into, which is El gato se sentó en la tapete, let's say we've already generated 3 words, El gato se, right? So we already have that as output. Remember, decoders generate 1 word at a time. So it generated El, then something happened, then it generated gato, then something happened, then generate se, then something happened. Now we're going to find out, how does it do it? How is it going to generate the 4th word? So we have this output so far, El gato se, right? So, and the output comes from the decoder part, from the top of the decoder. Remember, we have those probability distributions. That's where we'll be getting the output. So now we have this these 3 words, El gato se. What's going to happen is they're going to go back into the decoder at the bottom in Spanish. They're going to get their vector embeddings. So each one of these 3 words, El gato se, will have a semantically rich vector. So it'll have the dictionary meaning associated with it, or encoded in that vector. Then they will get the positional encoding on level 2. As we discussed, that's important. Then they'll go to level 3. The attention mechanism will happen among these same 3 words. So El gato se, these words will get to understand the context of what they have so far of this 3-word sentence. That context will be coded into the vectors for these words. After level 3 of the decoder, each one of these words will have a context-rich vector. So a Spanish context-rich vector with the Spanish sentence that we have so far of 3 words. Now it'll go into level 3B. And this is where the interesting thing will happen. This is kind of like the biggest addition that we're doing today compared to the previous episode 747. So what's going to happen now is there's going to be cross attention. So we have these 3 Spanish vectors going into this level 3B. And at the same time, on the building on the left, we can see there's 6 vectors, 6 English vectors sitting. They're context rich, they're ready to go, right? So if we were not to look at the encoder at all, let's just imagine, forget about encoder. What will happen if these 3 vectors just keep going? There's no level 3B, they just keep going through the decoder. What will happen? Well, they'll go into the feed-forward neural network, then they'll go into the linear transformation and softmax. And as before, as with any large language model, they will, or GPT model, they will, or decoder only model, we will produce the next word, right? So they will produce the next word. So based on El gato se, that's like a prompt for what's the next word. The next word could be paro, like the cat stood. The next word could be relajo, the cat relaxed. The word could be escondió, the cat hid, right? Those are all valid next words. It like makes sense to put a verb next. And the like a decoder only model, like a large language model, would just produce this next word, which is great. It could create a whole sentence, but that would have nothing to do with the translation, right? We don't want it to create a sentence based, like it would just give us the next most likely word based on what it's seen in the Spanish language, in the corpus of text that is seen in the Spanish language. What we wanted to generate is not just the most likely next word. We wanted to generate the most likely next word based on what it's seen in its training data, but conditioned on the inputs in English that we gave it. So this is where this level 3B, the cross attention, comes in. So let's rewind. These Spanish words went through level 1, through level 2, through level 3, through the normal attention. Now they come into this cross attention. What happens here is that from each one of the vectors that we already have context-rich vectors for these Spanish words. From each one of these vectors, we're going to create 3 vectors. We're going to create actually not 3. We're going to create 1 vector. So normally in attention, we create QKV, but in this time, we're just going to create the Q vector. So for each one of the Spanish words, we will have a Q vector created. And the KV vectors, instead of creating them from the same Spanish words, we're going to create them from the English words sitting at the top of the encoder, right? We have those 6 English context-rich words on the left in the image. Instead of creating QKV vectors from each one, we're just going to create the K and V vectors. So now we have, now we can.
Okay. I'm just gonna interrupt you for a
Go
second,
ahead.
so I can kind of. This seems like a pivotal moment. So I'm going to kind of recap, and you can confirm for me that I'm getting this right.
Sure.
So we've got 2 kind of buildings next to each other, or 2 or 1 structure with slightly different heights right next to each other. So I guess maybe it's kind of easier to think of like two buildings next to each other because they can have like their separate elevator systems or whatever. And so on the left we have the encoder,
Yes.
which is 4 stories,
Hmm.
and that's completely new in terms of what we've been talking about on this podcast. In episode number 747, we only talked about the right-hand building, which had 5 stories. Now we've got this building on the left, which has 4, but we've also, in order to allow these two buildings to communicate effectively with each other, you've added in an extra floor, 3B, between the 3rd floor and the 4th floor on the right-hand decoder building.
Correct.
So, um, as so we have flowing up the kind of the elevator on the encoder building on the left is the English
Yes.
language that we want to have translated into
Yes.
Spanish. And then on the right-hand side, there is Spanish language flowing upwards as well. And then they meet at this 3B. So information flows from left to right from the 4th floor, the top floor of the left-hand
Hmm.
encoder tower. It flows into level 3B of the decoder tower. And that's where this self-attention, this powerful thing is happening where
Cross attention.
the cue cross attention, where yes, right. So the self-attention is within one tower
Yes.
itself. So the decoder has self-attention. That's a really key
Yeah.
thing here. Thank you. Yes.
And
So
the
the
encoder
decoder,
has
yeah,
self-attention as well, its own self.
has its own self-attention. And that was level
Yes.
3 in both.
Self-attention is always level 3.
Nice. And then now in this 3B on the right-hand side decoder, we've got cross attention, which is blending the vectors, the Q, K, and V vectors that we recapped. And again, you can get tons of information on those from the preceding episode that Kirill was on, episode number 747. But it's the Q vector, the query vector, comes from the encoder, the left-hand
No,
side.
no,
In
from the
this case, our
decoder. Q vector comes from
oh,
the
from the
decoder.
decoder.
Because the
Q vector
Spanish
from the
words
decoder. Yeah.
need the context. And the
Right,
Q
right,
vector
right,
is the
right, right,
query.
right,
It's like,
right.
I need this context. Do you have it? I need this context. Do you have it? That's the Q vector. So that is in the right side.
Nice. Q vector is on the right,
Yeah.
on the Spanish
Yeah.
side in the decoder, and then the K and the V are on the left on the encoder.
Correct.
Nice. Okay, and so those blend together, and so it's a beautiful thing. So it's allowing that same kind of structure, these 3 vectors, the Q, the K, and the V, which previously, as we learned about in the self-attention, allowing us to figure out what the next token should be appropriately. Now we're getting, yeah, that same kind of mechanism, but being applied across these 2 different sources of information and blending them together so that you're getting context from one side. And how would you describe? Could you describe? So if Q is the context, no,
Q's,
K and V is the
yes.
context.
K is the key and V is the value that contains the context.
Yeah, yeah. So then, how could you? Is there like a way that we could sum up the Q side as like the complement to context? Like,
It's hard. It's hard to say. It's just a mechanism, really. I would say the context is inside the V vectors. The Q and K is just an indexing mechanism. It's like Q. This is what I'm interested in. Like, tell me about. I'm gonna add like human interpretation to this. Obviously, the transformer doesn't do this, but just for argument's sake, let's say the word we have el gato se, right? So the word se is like, oh, I'm curious about what action is being performed. I need context about a verb. Give me context about a verb. So the Q value in human understanding would be like, oh, I'm looking for verbs. And then on the encoder side, we've got the 6 English words. The cat sat on the mat. And so they have the K vectors. Again, this is butchering it, but it's very approximate, but it's better for understanding. Each one of those K vectors is going to have information. What context do I have? And so maybe the word cat, it'll have a K vector saying I'm a noun, and the cat sat. The word sad has the K vector saying I'm a verb. I've got a verb inside here. If you want to look for a verb, look in here. Sat on the mat, and then the word mad has the K vector saying, oh, I'm a subject or I'm an object. Like the cat might have I'm a subject, I'm a noun, and I'm a subject. The word mat might have I'm a object, and I'm a noun, and I'm an object. And then the word the is like I'm an article. If you need information on articles, look inside here. And so the Q vector for the word se, which is like, as I understand in Spanish, it's the start of a verb, but it's like, what's the next verb? What's the next verb? What's the context for this whole situation? It goes and it's like, I need a verb. And it goes across these K vectors like, no, you're not a verb. You're not a verb. Oh, you got a verb inside. Let me look inside the V vector for the word sat. And inside sat is like, oh, I'm a verb for sitting down. This is what it feels like, blah, blah, blah. And that's where the Q kind of query, it communicates through dot product with the K vectors of what it's looking for. When it finds a match, boom, it looks for the V, which contains the context that it needs.
Beautiful, man. You've really got this down now. I feel like, I mean, you obviously had it down even when we recorded 747, but it is very tight for you in your mind. It's like second nature.
Thanks, man. Thanks. Spent 6 months on this instead. I thought it was going to take 4 weeks. It took 6 months. It's literally been 6 months now. But I'm very glad. I'm very glad that got through this. Yeah.
Okay, yeah. So I derailed you as you were
No, that was
describing
really good to
the cross
clarify.
attention.
Thank you. And I didn't have this example in mind to share about. I just came up with this now about the verb, the noun, and so on. I think that was very helpful. What I wanted to add, I love your elevator analogy. So we have the two systems, the building on the left, the elevator goes all the way to level 4. There's a small little bridge from level 4 of the encoder on the left to the 3B level on the decoder on the right. That's where the values, the KV values walk across, and they, as you said, they blend with the Q values. A very important point is that the elevator on the encoder works only once. It's a one-way, one-off elevator. So the English words get in to the encoder and they go room to the top and they sit there. It doesn't happen every time. And this is like, I love these podcasts because they force me to think, like, go outside my comfort area and like force like the barriers. Like I figured this out yesterday. I was like, all right, I've learned transformers for 5 months. I know what I'm gonna say. Do I even need to prepare? And I sat down and prepared anyway. And I thought the elevator keeps going up every time and you were just hearing it. But no, it goes up once and they sit there. Why would it need to go up every time, right? It's the same 6 words. Your input English sentence doesn't change. So it makes sense. So these 6 words get into the encoder. They go up the elevator, they sit at the top, and they have these 6 context-rich vectors that are used again and again and again.
I think it's also a really good point to make that about the elevator only going up once, because that's the whole idea of the compute efficiency of this.
Yes.
So something that you mentioned, going back to that attention is all you need paper and the 8 different authors, they were specifically working together to come up with a computationally efficient mechanism that would work well on modern GPUs. And the elevator only going up once is a great example of how you're going to get more compute efficiency from this process.
So that's absolutely correct in terms of compute efficiency. So now let's recap what we have. So we have el gato se, these 3 Spanish words, right? So on the left, we have the English words that went up the encoder and they're sitting there. That happens only once up that elevator. They're we have these context-rich vectors. We'll call them O vectors. Now on the right, we have these 3 Spanish words. They go from level 1 through level 2. Then they go through the self-attention mechanism in level 3, where they get QKV vectors. Through that mechanism, each word gets a context-rich vector. Let's call those vectors A. Now, at the end of level 3, we have 3 context-rich vectors, which are vectors A, for one for each word. And then all of those vectors A go into this cross-attention mechanism, level 3B. So we have, on the one hand, we have the O vectors from the encoder, the output of the encoder, 6 of those vectors, right? So the English sentence. And then we have the A vectors for the 3 words in Spanish. And all of that is going to get merged in the cross-attention. By merged, what we mean is that from each A vector, we will create only Q vectors, right? So the K and V vectors are not even computed. So only Q vectors are computed from the A vectors inside the decoder side of things. So we'll have 1 Q vector for every Spanish word. And then on the English side of things, the Q vectors are not computed, but the K and V vectors are computed. So we'll have a K and V vector for every English word. As we just discussed, the cross-attention mechanism will happen. And from there, the Q vectors will look for the context they need using the K vectors. They'll find it, and the context will be taken from the V vectors. And from that, we will create new context-rich representations in the decoder side of things for each one of the Spanish words. So now we will have, let's call them vectors B. right? Because it came out of level 3B, we have a B vector for the word L, a B vector for the word gato, and a B vector for the word se. Now, these B vectors, they take into account the context that came from the English sentence. And from here, everything is the same. So now these B vectors, as before, the B vectors go through the feed-forward neural network. Each one of them goes through the feed-forward neural network. And then each one of them goes through the linear transformation and softmax to get the output. So from each one of the Spanish words, right? So we had el gato se. From each one of them, we'll get a what's it called? Probability distribution with 200,000 values, or however many 100,000 words there are in the Spanish language. And we'll throw away the first two, as we did previously. We'll throw away all of the probability distribution except for the last one, which in this case is the one that we derived from the word se. And we'll apply that probability distribution of 200,000 or however many values to all of the words or tokens in the Spanish language. And that will give us the probabilities for them. Basically, we'll know which word, the one with the highest probability, is the one that we're going to use next. And in this case, it's not going to be the paro, it's not going to be stood or relaxed or hit, right? Paro, relajo, escondido. We know because this generation is now constrained or conditioned on the English language sentence. Now there's no choice for the decoder but to say that the next word is going to be sento, right? The prediction is going to be that the cat sat on the mat, right? It can't say if the word sentence input sentence in English is the cat sat on the mat. It wouldn't be able to say that in Spanish that the cat relaxed on the mat, because that would be contradictory to the context that it got from the English sentence. And that's basically how it works. So the best way to think about the full transformer model is imagine it as just a decoder only model that's generating text, but because of that level 3B that we added in, it's generating text based on what it's seen in training data in that language, but that text has to be conditioned on the input sentence we gave it in the original language. And that's all it is.